Hello, my name is Lior Shamir, and I would like to share with you today something that I've been working on for well over a decade, which is a single observation that can explain several tensions, several anomalies that we have now in cosmology. And it's an empirical observation, so it's not a theory, but something empirical, something that we can actually measure, we can actually see. And let me show you what it is. So the idea basically is pretty simple. A galaxy that rotate in the same direction as the Milky Way is expected to have slightly different brightness, slightly different magnitude compared to a galaxy that rotate in the opposite direction relative to the Milky Way, and that's because of the Doppler-shift effect. But the thing is that the Doppler-shift effect is expected to be relatively small because the rotational velocity of galaxies is not large enough to make a substantial difference between galaxies that rotate in opposite direction relative to the Milky Way, and that is something that is expected. But when we look at it, when we try to measure that empirically, we see something a little bit different. And here's an example. That's from the DESI Legacy survey. So we have a lot of galaxies here, well over 100,000 galaxies here, both from the northern hemisphere and the southern hemisphere. The DESI Legacy survey has a very large footprint. And what we see here that when we compare the average brightness of galaxies that rotate in the same direction relative to the Milky Way, we see that is significantly different from the average magnitude of galaxies that rotate in the opposite direction. We expect it to be more or less the same within statistical fluctuations. Obviously, we expect it to be more or less the same, but it's not the same, and it's significantly not the same. And that is not something that we necessarily expect. We see it both in the northern galactic pole and the southern galactic pole, so both agree the difference is inverse, obviously, because the poles are inverse, but that's completely expected. Both poles here agree and give the same observation. But also when we look at other telescopes, and I did it to here we see an example of with Sloan and Hubble Space Telescope, both showing the same thing. I did it also with Pan-STARRS. You can see it in one of those papers that are listed below. And so no matter what telescope you're using, we're going to see exactly the same thing. In all cases, galaxies that rotate in the same direction as the Milky Way are a little bit brighter, a little bit different magnitude compared to galaxies that rotate in the opposite direction. And that's something that is not necessarily explained, but it can explain several different tensions, and I will explain later here. That's an example with Galaxy Zoo. So Galaxy Zoo is a data that was annotated, the direction of the galaxies were annotated by anonymous volunteers. So it's not the cleanest data. It's a pretty old data. It's not the cleanest. It's not the best data, but it still shows the same thing. It still shows exactly the same thing as the other experiments. And the funny thing here is that the data has been available for about 15 years, and it takes about 5 or 10 minutes to test the brightness, the average brightness, and compare that. Just nobody ever tried to do that comparison. Nobody ever tried to compare the brightness of galaxies that rotate in opposite directions. Yes, nobody thought that there could be a difference there. But if you do it, if you spend like the 5 or 10 minutes to run the query, you'll see it very easily by yourselves. That's the physics of it. So, like I mentioned before, because of the Doppler shift effect, we expect slight difference in the magnitude of galaxies that rotate in opposite direction relative to the Milky Way. But it's expected to be very small. The magnitude difference is expected to see, you can see here, about 0.006 of magnitude, which is very small. What we observe practically is much larger, and what we observe fits rotational velocity of about 5 to 10 times faster than the rotational velocity of the Milky Way. And that is something that could indicate that there's something that we don't fully understand about the physics of galaxy rotation, but we already know that we don't fully understand the physics of galaxy rotation, that many things are don't make perfect sense based on the physics that we know, and we can say that maybe it's dark matter, maybe it's MOND, maybe it's other things, but we know that we don't understand everything about the physics of galaxy rotation. Probably there are more things that we also don't don't understand about it. And that's one observation. It could be another piece in the puzzle to fully understand what's really happening in the physics of galaxy rotation. Now, if galaxies that spin in the same direction relative to the Milky Way have different brightness compared to galaxies spinning in the opposite direction, then that should be exhibited to an Earth-based observer as a difference in the number of galaxies based on their spin direction. So if you observe galaxies and we count them, we count galaxies that spin in one way compared to galaxies that spin in the opposite way, we expect to see a number that is not exactly the same, a slight difference. And that actually has been reported since the 1980s. Starting in the middle 1980s, they counted the galaxies and they found that with 92% confidence that the number is not the same. And then there were other experiments. 2011, the experiment was an experiment by Longo, about 15,000 galaxies. Again, not a very high number of galaxies, but it shows a very strong asymmetry between the number of galaxies spinning in opposite directions. And then other experiments at around the same time and also later. And in fact, every single telescope, every single sky survey that has enough data, collected enough data, shows exactly the same thing. You can see it here, and you can see it in the papers mentioned on the left. And you can see that all of these telescopes, the Dark Energy Survey, or this Legacy Survey of Pan-STARRS, or Hubble Space Telescope, or Sloan, they all show more or less the same thing. They all show asymmetry, and the axis, the dipole axis formed by the galaxy spin direction, it peaks about the same part of the sky for all of them. And that's interesting, because we can see it here. These are the peaks of the most likely dipole axis in the different experiment, and they're not exactly on the galactic pole. We don't expect that. There's always some statistical fluctuation there, but they're all around the galactic pole, and we can assume that maybe the galactic pole has something to do with that. And again, if the brightness of the galaxy depends on the relative location compared to the galactic pole, then we expect it. It's completely expected that the pole would peak at around the galactic pole. And here's another experiment that I like a little bit better, because here that's direct measurement. So we use the DESI Legacy Survey here with 1.3 million galaxies, very large footprint, both the northern hemisphere, the southern hemisphere. So it's the DESI Legacy Survey has a large footprint. And what we have is that's not a statistical analysis, that's direct measurements. So that's not an attempt to fit the distribution of the galaxies into some statistical model. That is either direct observation, the population, the number, the difference in the number of galaxies that spin in one way compared to the galaxies that spin in the opposite way. And we can clearly see that there are two hemispheres here. And we can also see here something very close to the galactic plane. And of course, that can be a coincidence, but not necessarily. It can also lead to the indication that the difference in the population that we see is related to the galactic pole, and which is related, like I showed before, to the motion, to the rotational velocity of the galaxies relative to the Milky Way. So the number of galaxies in the universe is actually the same, but what we see from Earth, because the galaxies that rotate in the opposite direction relative to the Milky Way are slightly brighter, we will see slightly higher number of galaxies that way. That will lead to the asymmetry that would peak around the galactic pole, like we see here. Over the years, there were some studies that showed that the distribution of galaxies, the spin direction of galaxies in the universe is random. So I'd like to spend maybe a few minutes to go over some of those. So in 2008, there was the Galaxy Zoo experiment, and not the best data. It's an old data. They didn't have all these algorithms that we have today. But what they had there, they had about 11,000 galaxies that were also mirrored. And they needed to mirror the galaxies because they use human volunteers and they have some perceptual bias. So by mirroring the galaxies, that offsets for the perceptual bias, and it leads to a valid data set that we can use. And they just say that they didn't find anything statistically significant, and they just concluded with that. But they don't show a p-value, and they don't show in the paper statistical analysis. When you do the statistical analysis with the same data that is in the paper, you see that the p-value is not necessarily statistically insignificant. It's not a very strong p-value again because the number of galaxies is not very high, but it's clearly not in disagreement with what I just showed. It's agree with what I just saw much more than it disagrees with it, and actually it supports it. Another experiment from 2017. That experiment used automatic annotation of the galaxies, much higher number of galaxies, so it was a stronger experiment. They had several experiments in that paper. The one that showed random distribution, they used machine learning to annotate the galaxies. And when you read the paper very carefully, you see that they say that they manually removed all the features, the machine learning features, that correlate with the spin direction of the galaxy. And that obviously, when you force that, when you manually remove these features, you obviously naturally remove the ability of the machine learning algorithm to identify the spin direction, to be sensitive to the spin direction, and that leads to random distribution. And in the paper, they don't explain why they removed these features manually, but they just say that they did it. And with my student, we reproduced that experiment without removing any features manually, just using everything that's in the experiment, and also without using machine learning at all. Machine learning, it's never a good idea to use machine learning in experiments like this. Machine learning has all sorts of biases. But we reproduced the experiment, and the result is what you see here, the graph that you see here. You can see the details in the paper there. But what we see is a very clear, very strong signal, and it peaks very close to the galactic pole, as you can see here. And the third experiment, probably the weirdest one, is again using Sloan galaxies to show that the distribution is random. And there's some inaccuracies in the paper, and it's addressed in that PSJ paper that you see here, so everything is described there. But in summary, the reason they got to random distribution is they have two things. One is that they used three-dimensional analysis. I used the two-dimensional analysis in what I showed you. They use a three-dimensional analysis, so the galaxies also need the redshift, but the galaxies don't have spectra, so they use the photometric redshift. And the photometric redshift is very inaccurate. So when you try to find a signal of 1 or 2% in an error that has about 15%, which is the error of the photometric redshift, then you're very naturally expected to get random distribution, because the noise is far stronger than the signal that you're looking for. The other reason is that is not mentioned in the paper is that they assume that the galaxies, the Sloan galaxies, are distributed uniformly in the hemisphere. And that assumption is not necessarily correct. Actually, it's not at all correct. The Sloan galaxies are not nearly distributed uniformly, and to get to a uniform distribution, they had to shift the galaxies in the hemisphere, which further reduced the signal. And that's not in the paper. To get that, you need to contact the institution and ask them why you can't reproduce it, and then they tell you, to reproduce it, you need to assume that the galaxies are uniformly distributed in the hemisphere. So everything is in the paper, and also in the URL, there's the whole reproduction of the experiment with the data, with the code, and you can reproduce all of that. So that leads us to the Hubble tension. So the HO tension, the HO computed with the CMB is different from the HO computed with the supernovae, with 1A supernovae. And the question is why that happens. It could be explained, but maybe we don't know something about the universe. The other explanation that maybe we don't know something about one of the measurements, and that's what I argue here. Because 1A supernovae, they rotate with the galaxies. They inherit the rotational velocity of the star that they were created from, so they inherit the rotational velocity of their host galaxy. So if the Doppler-shift effect is greater than what we expect, then the brightness of the galaxies will have a systematic bias in the brightness of the supernovae, of the 1A supernovae that we observe, and that will directly lead to a systematic bias in the distance, and that would directly lead to a different HO and therefore HO tension. So what I did to test that, I used the work of these people. So what's good about it is that they share the code and the data, very easy to reproduce the experiment that they have, and then do other experiments based on that. So what I did, I used the same experiment, the same data. It's a pretty commonly used data set, 1A supernovae, and I only used supernovae that rotate in the same direction relative to the Milky Way. Here's the result. So we can see when we use all of the data set that they had, we get an HO of 73.75, which is close to what they show in the paper, which is in tension with the HO compared with the CMB. But when we only use supernovae that rotate in the same direction relative to the Milky Way, HO drops dramatically to 69. And that almost solves the tension completely. It doesn't solve it completely, but it's not expected to solve it completely because those supernovae, they're not exactly on the galactic pole, and the inclination of their host galaxies is not exactly 90 degrees, and the rotational velocity is not exactly the same as the rotational velocity of the Milky Way. So there should be some tension. We expect to see some tension there, some Doppler-shift effect, I mean. So there will be a little bit of a tension, but much less than we just use all galaxies without normalizing for the rotational velocity at all. And when you use just supernovae that rotate in an opposite direction relative to the Milky Way, not just that the HO doesn't reduce, it even increases. It even increases to 74.2, which is a higher tension, which is also expected because when using just supernovae that rotate in the opposite direction, the Doppler shift effect should get larger. So that's it. If you have comments or ideas or questions or want to discuss, I'll be happy to do it during the sessions. Or if not, then also in private in any other mean. So yeah, thank you for listening.